Hey guys, welcome to video 65. Today we're going to work out the problem I left at the end of the previous video. Here's the circuit. It's a 6AN8 Pentode, and we're going to set up a Q point with a plate current of 2.5 milliamps and a VPK of 125 volts. And we're using a screen grid bias of 75 volts this time. So the first thing we want to do is come over to our plate curves and locate the Q point. And that's 2.5 milliamps by 125 volts. So here's our Q point right here. And let's estimate the required grid voltage to establish this Q point. So let's see, we're pretty close to negative 1.5. So let's just estimate this to be VGK of approximately negative 1.4 volts. Next, I'm going to determine the screen grid current, and we'll just use the rule of thumb where I sub s is approximately equal to 0.25 times the plate current, so that's 0.25 times 2.5 milliamps, which is 0.625 milliamps. Then our cathode current, I sub k, is IP plus IS, so that's 2.5 milliamps plus 0.625 milliamps, and that's about 3.1 milliamps. So let me fill that in here, 3.1 milliamps, and we're after a voltage drop of 1.4 volts across R sub k. So now we can determine that value. R sub k is 1.4 volts divided by 3.1 milliamps, and that's 452 ohms, and we have a pretty close standard value of 470 ohms, so let's go with that, 470 ohms. And now we want to determine our plate resistor value. The drop across RP is going to be approximately VPP minus VPK, so that's 250 minus 125 is 125 volts. So R sub P is equal to 125 volts divided by the plate current, 2.5 milliamps, and that's 50 k ohms, and we do have a close standard value of 47 k ohms, and we'll go with that. So here we are, 47 k ohms. Okay, next let's determine the value of RS, our screen grid resistor. We're after a screen bias voltage of 75 volts, so that means that we're going to have a drop across RS of 250 volts minus 75, which is 175 volts. We know our screen grid current is 0.625 milliamps, so R sub S is equal to 175 volts divided by 0.625 milliamps, and that works out to be 280 k ohms. And again, we have a pretty close standard value of 270 k, so that's what we're going to go with. We'll set RS to 270 k, and we're just about there. We need to pick a grid resistor, and again I'll just go with 1 meg ohm. And the next thing we want to do is determine our coupling and bypass caps, and like before, I'm going to save the details of calculating those values for another video. For right now, we're going to set C1 equal to 0.1 microfarads, our cathode bypass cap 100 microfarads, our output coupling cap, let's make it 10 microfarads, and C4, we could use just about any value from around probably 0.1 microfarads up, but I'll just make it the same as C2. Let's just go with 10 microfarads. And there we go. There's our design. It's very messy, but I'm going to give you a nice, neat version of this momentarily. And through the magic of editing, I've cleaned up half the screen, and here is our nice circuit. I'm going to move this over just a little bit to maximize my workspace here, and now we'll get to work on the load lines. Let's start with our DC load line and VPK cutoff, which is VPP. That's 250 volts. Let's mark that point right here. And then IP SAT, which is going to be approximately VPP over RP. And I'm going to use the ideal value. We'd have chosen 50K to make things work out nice. So that's 250 volts divided by 50K ohms. And that is 5 milliamps. So let's mark 5 milliamps over here. And we'll connect these points. And here is our DC load line. So next we'll do our AC load line, but first we need to determine R prime L, which is our AC load resistance, and that's RP in parallel with RL. So we've got 47K in parallel with 100K, and that works out to be about 32 K ohms. So now we can find our endpoints for the AC load line. Come down here. IP SAT is IPQ plus VPKQ divided by R prime L. So that's 2.5 milliamps plus 125 volts divided by 32K. So we've got 2.5 milliamps plus 3.9 milliamps, and that is 6.4 milliamps. So there's our plate saturation current. Then VPK in cutoff is going to be VPKQ plus IPQ times R prime L. So we've got 125 volts plus 2.5 mils, 2.5 mils times 32 K ohms, and this all works out to be about 205 volts. I'm a little bit tight for room, so I'll just skip a few of the intermediate calculations. So we've got 6.4 milliamps, which would be right about here, and 205 volts, which is right here. And let's use red for the AC load line. And here we go, connecting these endpoints. There it is. It goes right through the Q point as we expect. And now we can determine the maximum plate current and minimum plate to cathode voltage by finding the intersection of our AC load line with our VG1 equals 0 curve. So let me make a mark here at this intersection, and we're pretty darn close to 6 milliamps for our maximum plate current. So that would be lowercase IP max is about 6 milliamps. And let's see if we come down here. Oh, it looks like about what, 5, 10, 15, maybe 16 or 17 volts. So our VPK minimum value, let's say that's approximately 17 volts. Okay, we're really getting tight on space again, so let me clear out a little bit of my rating up here, and now let's determine our maximum and minimum output voltage swings. Of course, VO max can be found by multiplying IPQ times R prime L. And that's the distance from our Q point to the end of the AC load line on the right hand side. That's VO max. And that works out to be 80 volts. And then VO min, our maximum negative output swing, is going to be the distance from VPKQ down to VPK minimum. Way over here it's 17 volts. So that is VPKQ minus VPK minimum. 125 volts minus 17 volts is 108 volts, but that's going to be negative, so it's negative 108 volts. And there we go. There's our essentially our unclipped output voltage swing, plus 80 volts minus 108 volts. Now I'm going to clear the decks one more time here, and then we'll do our small signal analysis. So let's just make some room, and that should do it. And let's change our color back to blue. And we're going to determine our R prime P, that's our AC model plate resistance, R prime P, which is dynamic plate resistance in parallel with external plate resistance, and our load resistance. So that's going to be 100K in parallel with 47K, and RL is also 100K, and that works out to be about 24.2 k ohms. And the next thing, let's do something easy. Let's find our input resistance, and that's simply RG. Rn is RG, which is 1 megohm. And let's see, how about our output resistance, RO? That's seen by our load looking back in, which is going to be the dynamic plate resistance in parallel with our external plate resistor. So that's 100K in parallel with 47K, and that's about 32 k ohms. And finally, our voltage gain, AV, is negative GM times R prime P. And let's see, GM is 4.5 millimos, negative 4.5 millimos, times 24.2 k ohms is a voltage gain of negative 109. Now, since this page has become almost incomprehensible, let's just go on over and take a look at the nice version of the calculations and the AC and DC load lines as well. So reviewing the small signal analysis, we've got Rn is 1 megohm, R out is 32 k ohms, our AC small signal model plate resistance is about 24.2 k, and our voltage gain works out to be about negative 109, which is pretty typical of Pentode based amplifiers. They're capable of very high voltage gain, as we can see here. Now over here are the AC load line calculations, and I've also labeled the values for VO max and VO min in relation to the AC load line as well. Now, as you guys know, I like to back up all of my theoretical calculations with experimental values because, you know, what good is all this stuff if it doesn't work? So let's go on down and I'll show you the results I got from building this. On the left-hand side, we've got the schematic with all of our design goal values, and on the right, I've tabulated those results with measurements taken for a 6AN8 from General Electric and one from RCA. These are new old stock vintage tubes, and as you can see, we got really good agreement with our theoretical values here. The voltage gain is right on the money, and in the case of the RCA tube, it's actually a little better than we predicted, which is always a nice thing. And if we go on over to the next page, I've got the scope capture for the General Electric 6AN8 I used an input voltage of 100 millivolts peak to peak. The output was about 10.9 volts peak to peak inverted. So the gain here was negative 109. And for the RCA tube, the input voltage was still 100 millivolts peak to peak at 1 kilohertz. The output was 11.5 volts peak to peak, so our gain here is negative 115. And you can see in the scope display there's no hint of distortion shown, so I didn't bother doing a spectrum analysis for either of these outputs. We've got a relatively small amplitude output, so it's going to be pretty clean. And finally, as promised, I've got the plate curves for the 6A and 8 with the fine grid lines added. Here are the curves for screen grid bias of 75 volts. So you can do a capture of this if you'd like to use it for design. And here are the curves for a grid bias of 100 volts. And that's all I've got for you today. So I'll catch you guys next time around.